Okay, let's talk about momentum and the impulse-momentum theorem. So this is our topic for Chapter 9. We're introducing a new concept called momentum. And momentum is got a very simple definition. It is simply the mass of an object times the velocity of that object. Because velocity is a vector quantity, momentum is also a vector quantity, and for reasons that are lost to me, the letter that we use to represent momentum is p. So little p equals m times v is the momentum of an object. It's in the same direction as the velocity of that object. So it's a very simple definition. Now, the momentum of a closed system is always conserved. And the idea of a closed system is the same that we had for conservation of energy. And the only way that the momentum of a system can be changed is if a force acts on it. And so we can quantify that by looking at by using Newton's second law in combination with the definition of momentum. So the momentum of a system is only changed if an external force, and that means external to the system, so we remember that Newton's second law says that force is equal to mass times acceleration, and that has a certain sort of similarity to momentum here. Momentum is mass times velocity, and we remember that acceleration is a change in velocity over some period of time. And so that says that the force is equal to mass times a delta v over delta t, which is mass over delta t times v final minus v initial, because remember that Greek letter delta means a change in a quantity. So here we've just redefined Newton's second, or not redefined it, but rewritten Newton's second law. And we've rewritten it to say that the force acting on something is equal to the mass of that something divided by the time over which that force is acting on it times the change in velocity. And if we write that out, I can multiply both sides by delta t. I get f delta t equals mvf minus mvi. Well, m times v is momentum. And here I've got an mvf, that would be the final momentum of that object, and mvi, that would be the initial momentum of that object. So this quantity here is simply the change in momentum of an object. So we now see that Newton's second law basically says the force acting on a system times the time that that force is acting on the system is equal to the change in momentum of that system. So the bottom half here is saying in equations what is said in the top half in words, that the momentum of a system is conserved. In other words, the change in momentum, delta p, is zero unless there's a force acting on it. And that's what we've got down here. If there's a force acting on it, that gives us a change in momentum. If there's no force acting on a system, then the momentum of that system doesn't change, no matter what is going on inside it. So if we have some force acting over a short period of time on an object, we call that an impulse. So impulse is some force times the time period that that force is acting on something. And the word impulse sort of conveys a notion of a short period of time. And in fact, we only use this if this is if delta t is small and it's a short blow of something like that. So like if a baseball bat hits a baseball, that would be an impulse. The bat exerts a force on the ball for some short period of time, delta t. We use the letter capital J to be the impulse, and because over that short period of time the force goes from 0 up to some maximum value back down to 0 again, it's not a constant value. We just can say we're going to take the average value of the force times the time, and that impulse then is equal to the change in momentum. Sorry about my handwriting again, but J equals delta P then is our impulse momentum theorem. The change in a system, the change in the momentum of a system can be approximated or can be calculated by computing the impulse of external forces acting on that system.